morning, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next topic of the subject for Unit 1. And the topic of today's lecture is DSB SE signal, its spectrum and some of its mathematical expression that we are going to derive. So, in the previous lecture we have discussed about what is DSB SE. DSB SE full form is double sideband suppressed carrier, which means that we have to transmit two sidebands only, and it consists of USB, that is upper sideband and lower sideband, and we are not going to transmit the carrier signal because in the normal type of amplitude modulation we are transmitting carrier signal, upper sideband and lower sideband, but in case of DSB SE, that is double sideband suppressed carrier, we are not transmitting the carrier signal. We are transmitting two sidebands. Why we are not transmitting the carrier signal? Because it does not carry any kind of information. It is just transmitted to provide the synchronization between the transmitter and receiver. So, this is the spectrum and this is the standard equation for DSB SE signal, that is MT. Now, MT is nothing, it is the message signal, that is the original form of signal, continuous time signal. This is multiplied by carrier signal, that is cos omega Ct. So, DSB SE signal is nothing, this is MT cos omega Ct. Now, according to this equation, this cosine term will be divided into two exponential terms. Let's say this is cos omega Ct, then it can be written as e to the power j omega Ct plus e to the power minus j omega Ct divided by 2 plus. So, this is the form of cos omega Ct, where you can write down this cosine term into two exponential terms, e to the power j omega Ct plus e to the power minus j omega Ct divided by 2. So, which means that we have in the spectrum, we can convert these two exponential terms into two frequency terms, and these are centered at frequency minus omega c and plus omega c, which is nothing, this is the carrier signal. So, upper sideband, you can see both at both the sides of the origin there will be upper sideband and lower sideband. In this case, this will be the upper sideband, this portion, and this will be the lower sideband. This is LSB and this is USB, upper sideband and lower sideband, and on the negative hand side there is also an USB and LSB. So, these are the two sidebands which are present across the origin. So, this is DSB SE signal. Now, next is the waveform. Now, corresponding to this MT cos omega Ct, we can also draw its waveform, and this waveform is, in this case we have to change the amplitude of the carrier signal proportional to the amplitude of message signal. Now, the instantaneous value of the message signal, we can consider the instantaneous value of MT also here. So, you can see that this is the dashed line and this is nothing, this is the envelope of MT which is being shown over here, and this line, this waveform which is been fitted inside this particular dashed line is known as MT cos omega Ct. Because cosine signal is itself a high frequency signal, its amplitude has to be fixed between this particular signal. So, that is the resulting, this whole resulting waveform is known as MT cos omega Ct, that is DSB SE waveform. Now, next is some mathematics or some of the expression that is related to DSB SE. So, for this MT cos omega Ct, which is the standard form of the DSB SE signal in time domain, we have to convert this into frequency domain, and we have to take the Fourier transform. This sign shows the Fourier transform of this MT cos omega Ct. Now, taking its Fourier transform, since this cos omega Ct will be broken into two exponential terms, that is e to the power j omega Ct plus e to the power minus j omega Ct by 2. So, due to that, there are two terms which comes into picture. First one is LSB, other one is USB, and its amplitude will be half. Corresponding to this, there are two spectrums which are plotted, one at the left hand side of the origin, other at the right hand side of the origin. Its center frequency is Fc, this is Fc plus Fm, that is upper sideband, this is Fc minus Fm. that is lower sideband. So this will be the upper sideband and this will be the lower sideband, and on the left hand side there is also, this is upper sideband, this is lower sideband. And the bandwidth, one thing that you have to keep in mind about the bandwidth of the DSP-SC signal. Now if you are going to subtract this particular waveform, this frequency, let's say this is FC plus FM, subtract this from C minus FM. So the bandwidth will be is equals to FC plus FM minus FC plus FM, and you can cancel this FC term. So the bandwidth will be equivalent to 2 FM. So this is the standard bandwidth of DSP-SC signal, which is same as the DSB signal, that is double sideband. The bandwidth will be same, but the power is saved in case of DSP-SC signal, because whatever power you are using to transmit the carrier signal is saved, because you are not transmitting the carrier signal because it is of no use. Now next is the DSP-SC modulator. So there we are going to study 2-3 types of modulators. So the first one is the balanced modulator. Balanced modulator is nothing, it is a kind of product modulator where you are going to multiply the incoming signals. So this is the amplitude modulator. Amplitude modulator can be drawn using BJT, or it can be drawn using diode also, because diode is a non-linear device. So the incoming signal of this amplitude modulator is AC cos omega CT and minus MT. So when it is multiplied, we will get this AC 1 plus MT cos omega CT plus MT. So this will be the message signal, and this is the carrier and amplitude modulated signal. So there here we are getting 3 terms, that is carrier signal, we are getting message signal, and other we are getting the modulated signal in the upper half of this block diagram. In the lower half also we are getting the 3 terms, that is carrier signal, message signal and the modulated signal. Now these 2 signals are added together and we are going to receive, or we are going to transmit the amplitude modulated signal, that is DSP-SC signal, whose amplitude is 2 AC multiplied by MT cos omega CT. So, now showing how the outputs of the 2 amplitude modulators are combined to produce a double sideband suppressed carrier output. So this is the balanced modulator block diagram. Now next we will see the nonlinear type of modulator. So in the previous figure, amplitude modulator, it is replaced by a nonlinear device. Now nonlinear device is nothing, it is a diode, because it is having a nonlinear IV characteristics, that is current voltage characteristics of a particular diode is nonlinear in nature. So it is very easy to design any modulator using this diode. Now this will be the current voltage equation. Wt is equals to AVT plus V square T. So we can find out the output of the first block is given by this equation, that is V1T is equals to MT plus cos omega CT, and second block is V2T is equals to MT. This is V2T is equals to MT cos omega CT. So these are the 2 equations. So we can add these 2 equations by putting this in particular block diagram, where Vt is replaced by V1T minus V2T. Same here, and then after simplifying this equation, because after putting this value like MT plus cos omega CT minus MT cos omega CT, we can get this one, and then this will be the value. So after passing through this particular equation, simplified equation, through a band pass filter, the final value or the final mathematical expression for the DSP-SC modulator is 4B MT cos omega CT, where 4B is nothing, it is the multiplying factor or just a constant. B can be any constant value. So that will be 4B MT cos omega CT. So that is the band pass filtering DSP-SC output. Now next we will see, now this is the DSP-SC modulator third type, that is a switching modulator, and it is also known as ring modulator. This is also known as ring modulator because we are using 4 diodes over here that is connected in a ring form, and here in the center we are applying a carrier signal whose value is A cos omega ct, and 4 diodes are connected in a ring form. So another thing that you have to keep in mind that at every modulator side we are using band pass filter, and at the demodulator side we are using a low pass filter. So this is a switching modulator where empty is the message signal. This is a switch which is being switched on and off depending on the values of the carrier signal, and this is a band pass filter. At the output of the band pass filter we are having this signal that is kmt cos omega ct. So figure A is the DSB-SC generation using switching circuit, and B is the itself is a switching circuit. So ST signal can be written as half plus 2 by pi cos omega ct minus 1 upon 3 cos 3 omega ct plus 1 upon 5 cos 5 omega ct minus 1 upon 7. So this can be extended, and you can see that there are odd terms are there like 1 omega ct, 3 omega ct, 5, 7, then 9, 11 with an alternate sign plus minus plus minus. So that is the expansion of this particular equation. Now yt will be is equivalent to mt multiplied by this particular signal that is st. So mt multiplied by this whole equation. So at the output we are having this particular equation that is 2 by pi mt cos omega ct. Now you can see in all the 3 modulators this mt cos omega ct is a constant term that is fixed, only the multiplying factor will be changed. So here it will be 2 by pi, in the previous case it will be 4b. So that is how the multiplying factor will change, but the output will be same, that is mt cos omega ct. That is the standard equation for DSB-SC modulator. Now next comes the DSB-SC demodulator. So the first type of DSB-SC demodulator is a coherent detection. Now what is coherent detection? Like I have said that why carrier signal is sent. Carrier signal is only transmitted just to synchronize the local oscillator used at both sides, that is at the transmitter side and at the receiver side. So coherent detection is known when both the carrier signal are having same phase and frequency. If it is not having the same phase and frequency, then the demodulated output will not be same. So that is the coherent detection. Now coherent detection we are going to see this in detail. The reverse frequency translation by multiplying with the carrier and then low pass filtering. So what we are using the concept in coherent detection is we are just going to multiply the received signal with the locally generated carrier signal. So mt cos omega ct is the standard form of the DSB-SC signal. It has to be multiplied by this carrier signal that is locally generated. This and the carrier signal which is generated at the transmitter side, both should have the same phase and frequency. So mt cos omega ct should be multiplied by cos omega ct. So we are getting this cos square theta term. So cos square theta can be divided into two terms, that is 1 plus cos 2 omega ct by 2. So that will be mt half plus half cos 2 omega ct. So we are going to multiply this. So mt by 2 plus mt by 2 cos 2 omega ct. Now as I have told you that at the receiver side we have to use a low pass filter. So when the low pass filter is used, then this high frequency term that is 2 omega c will be filtered out. We are just getting the mt by 2 term. So the low pass filter which is used at the receiver side should have the center frequency or the cutoff frequency equals to omega c. So it will, if there is any term that is cos omega ct, then that will be passed. Only the higher frequency term that is greater than omega c will not be passed. So only this term will remain, and that is the desired situation where we want only the message signal. The only thing is that its amplitude is reduced by half. So that is okay because it is due to the effect of noise that will going to affect the quality of the signal at the channel. Now if the local carrier has phase shift theta with respect to original, then from above demodulated message, that is empty cos theta is there. So no message is there for theta is equals to pi by 2 also with the phase amplitude changes. So and if the carrier, so there are two situations are there. If the local carrier frequency is different, that is fc plus delta f, means it is shifted by a factor, that is delta f, then the demodulated signal is proportional to empty cos 2 omega ct and has a change in and need to be precisely synchronous. So to synchronize the terms at the transmitter and the receiver side, we have to use the same local oscillator, which will produce the carrier signals having same phase and frequency both at the transmitter and receiver side. Now next is DSB-SC demodulator second type. So this is a squaring synchronizer. So obtaining the synchronous carrier from squaring, filtering and divided by 2. So there are three blocks that we have to use to generate the demodulated signal. So this is the received DSB-SC signal whose equation is given by A cos omega mt into cos omega ct. So it will be passed through a squaring circuit, means the square output will be generated over here. So this will be Si square t. You can see over here that it is written A square cos square omega mt into cos square omega ct. So it will be filtered at 2 fc, means it should be filtered at 2 omega c, then it will be passed through a divide by 2 device, means the frequency whichever we are getting, it has to be divided by 2, then it is synchronizing signal. So this will be A square 1 by 2 plus 1 by 2 cos 2 omega mt multiplied by 1 by 2 plus 1 by 2 cos 2 omega ct. So it will be equivalent to A square by 4 1 plus half cos 2 omega c plus omega mt plus half cos 2 omega c minus omega mt into cos 2 omega mt into cos 2 omega ct. So this is nothing, these two are the high frequency terms that we are getting over here. Now next comes the SSB-SC system. So in the previous section we have discussed about DSB-SC, three types of demodulators and two types of demodulators. Now we are going to discuss the SSB-SC signal. Now its full form is single sideband suppressed carrier, which means that we are either transmitting the upper sideband or we are transmitting the lower sideband, in this case that is SSB signal. So this is the waveform corresponding to the baseband signal. This will be the waveform that will be centered from minus 2 pi by b to plus 2 pi by b, means its bandwidth will be 2b. Then this will be the spectrum for the DSB. Now DSB is having only this is for DSB-SC, it is having only the two sidebands. We are not transmitting the carrier signals. So here this is upper sideband, this is lower sideband, this is centered at omega c, and on the negative hand side there will be minus omega c. This will be the upper sideband, this will be the lower sideband. Now if we want to transmit only the upper sideband, then this will be the spectrum, and when we only want to transmit the lower sideband, then this will be the spectrum. So this will be USB and this will be LSB. So when this particular signal, so up to here we have seen that these two are nothing, these are the SSB-SC case, one with upper sideband, the other is having with the lower sideband. Now it has to be multiplied by omega c and it will be demodulated by low pass filter. So this will be the centered frequency, this will be when this particular signal is multiplied by cos omega c, then another two terms are there, because there will be a cos square theta term will appear, because we are going to multiply cos theta with cos theta, and then 1 plus cos 2 theta is there. So there will be a term for minus 2 omega c and plus 2 omega c. So corresponding to that there are two spectrums which will going to arise. So that will be the final demodulated waveform. So that is the case for SSB-SC signal. Now next is the time domain representation of the SSB. Since we have seen the spectrum in time domain, this will be in case of frequency domain only. So this is nothing, this is the message signal waveform, its bandwidth is 2B. Next will be for the upper sideband, another is for the lower sideband. So in case of this particular waveform, that is the upper sideband, this will be m omega multiplied by u omega, and in the negative hand side, when we are transmitting only the LSB, then there will be m omega multiplied by u of minus omega. Now from here it is much more clear that how the equation of this particular LSB or USB will be derived. So in this particular spectrum, as you can see that this will be m plus omega minus omega c, this is m minus omega plus omega c. So when these two are added together, and this will be the USB term, because here there will be a cosine term, you can convert it into e to the power j omega ct and e to the power minus j omega ct. Now using this, it can also be solved to phi USB and LSB. Now a general SSB signal that has been written over here can be expressed as phi SSB t is equals to mt cos omega ct minus plus of mht sin omega ct. So this is nothing, this is the message signal multiplied by cos omega ct, and this is the Hilbert transform multiplied by the sin omega ct. Now this particular term, that is mht, how this will be generated? Now when this empty signal, that is the original message signal, is passed through a block, means when we are going to provide a 90-degree phase shift to the incoming signal, that is MT, we are having a Hilbert transform signal, that is MHT. When it is multiplied by this signal, that is again 90-degree phase shifted version of this locally generated carrier, then we are having this sin omega ct. So we have to multiply this MT cos omega ct with MHT sin omega ct. Now why these minus plus sign is there? In case of USB, that is upper sideband, we have to use a negative sign. In case of LSB, there will be a positive sign. So this is how we are going to generate only either the upper sideband or the lower sideband. Now next is a numerical that is related to SSB. So find phi SSB for a simple case of a tone modulation, that is when the modulating signal is a sinusoidal signal, that is mt cos omega mt. So this is the Hilbert's transform form of the input signal. Now you can see that mt is cos omega mt, and we have to take its Hilbert transform. So shifted by 90-degree, then we are getting this sin omega mt. So we have to put this particular equation in the standard form of equation. So mt will be cos omega mt into cos omega ct minus plus this mht, that is sin omega mt into sin omega ct. So this is cos a cos b minus plus sin a sin b. So this will be the formula for cos a plus b. This is the case for USB, this will be the equation. For LSB, this will be the equation. So this is a very simple numerical related to the SSB modulation. Now next is showing the spectrum, that is you can see that in case of message signal, two impulse functions are there at minus omega and plus omega m. In case of this DSB spectrum, there will be again two spectrums, one is at USB, there is LSB, this is USB, this is LSB. Now this is for the USB case, this is for the LSB case. So this is another form how you can going to show the spectrum of the SSB-SC signal. Next is the generation of SSB-SC. Now this is done using the selective filtering method. So DSB-SC signal is passed through a sharp cutoff filter. When this is passed, then half of the waveform will be filtered off, like either the USB is filtered off or LSB is filtered off. So this is done using the any selective filtering method. Next is the phase shift method. In this case, as you can see, according to the equation, that MT, when it is passed through pi by 2 phase shifter, then Hilbert transform, that MHT will be generated, and when cos omega CT is passed through a 90-degree phase shifter, then sin omega CT will be generated. And we are going to use two DSB-SC modulator, that is nothing, that is balanced modulator, product modulator, and we are having this SSB-SC signal. The equation we have already seen in the previous slides. And this is how we are going to demodulate by multiplying this signal with by a cos omega CT. Then higher frequency terms will be generated, then it is passed through a low pass filter and we are getting the final SSB-SC signal. Next is the envelope detection of the SSB-SC. Now, in case of this envelope detection, if the carrier amplitude is large enough, then MT can be recovered by this envelope detection. Now, this can be done by using, now envelope detection is a very important type of detector which is used in amplitude modulation also. So, this is the final equation for the envelope detection where we are using diode in case of demodulation, that is a nonlinear device. Then after simplifying, when we are considering when MT by A, that is nothing, that is the modulation index, when it is far less than 1, then this will be the envelope of the transmitted signal. So, in today's lecture we have discussed about DSB-SC and SSB-SC signal. Thank you.